to attend over this fall semester. We look forward to the spring semester coming up in late January, early February. We'll be hard at work putting together a new group of speakers. We will today, though, wrap up Book of Scientists for 2025 with Dr. Jim Green, former chief scientist at NASA, former Jim Adams boss. That probably was the harder job, and now a science consultant. We all know about local weather and how, it can rain or snow or the wind can blow. We also know about global weather effects like La Nina and La Nino, or those winds that form hurricanes and those sorts of things. We've also talked at Book of Scientists a lot about space weather and how the sun interacts with the earth and the two magnetic fields combine and churn and move particles around. But now Jim has this new concept that he's working on. And so he's bringing it to Book of Scientists. Actually, I think we're probably one of the first briefings he's given on the topic. And it's called cosmic weather. How does our solar system interact with the Milky Way, and how does that affect, or how did it affect, life on Earth? And so, Jim, the stage is yours.
All
And
right.
I am sure we're going to have lots of questions when you're done.
All right. Super. Let me go ahead and get started. Um, I'm assuming everyone sees the one chart on cosmic
Yep.
weather.
We've,
All right.
uh, we've got
Super.
your presenter view, though, Jim.
Ah, all right. Let me flip that. There we go. All right. So today we're going to indeed talk about cosmic weather. And this beautiful image that we're seeing here, uh, I enjoy because it just typifies all the concepts in cosmic weather. There are stars that have exploded. There are stars whose magnetic fields are plowing through other galactic nebula. We see high energy particles streaming up and down magnetic field lines. And it's just such a chaotic set of activity going on, as it seems, but it's all part of the evolution of stars that are around us, the evolution of our galaxy, and that all makes up what we call cosmic weather. So today we're going to talk a little bit about the birth of the solar system and the Earth, because cosmic weather is on timescales of thousands to millions to billions of years. All right, so we have to understand what's happened to the solar system and Earth from its birth. We'll touch briefly on today's space weather, so that everyone understands, we are in the atmosphere of the sun and we go through what we call space weather events all the time. In fact, aurora is a manifestation of space weather. That's what affects the Earth in many other ways, but for those people on the ground, that's one of the key effects. Then we'll talk about our heliosphere, and where our heliosphere is in the galaxy is in a cloud, and that cloud is called the local cloud. But we're going to be moving through the local cloud, and then we end up getting into the galactic environment, more of the galactic environment. Now, the local cloud is part of that galactic environment, but what's ahead of us? We'll also talk a little bit about what's behind us. What did we go through? And that means, what was the cosmic weather like in the history of the sun and our solar system? Okay, so 4.5 billion years ago, some sort of ripple occurred in a large molecular cloud that we lived in, that we come from, rather. And that ripple caused islands of mass to accumulate, which then attracted more material. And as these things swirled around, we ended up with this cloud collapsing into a number of stars. Now, we believe our birth cluster was anywhere between 2,000 and 20,000 stars. All right. So there's a huge number of stars that were generated at the same time our sun was. Now, since then, since we've moved around the galaxy, many of these birth stars have dissipated and moved off in other directions, although we have started to identify only a few of them. As the cloud collapses, it actually conserves angular momentum by ending up creating a disk. And in this disk, then we concentrate a volume of material into a thin area, which then is available to accrete other things. In addition to our sun, which would be the center of the collapsing disk, the dust that's in this area begins to stick, and this dust then begins to accumulate into larger and larger pieces, into what we call planetesimals. These are asteroid-sized objects, and as they collide and create even bigger objects, which then heat the whole object and melt it, and where the heavy stuff moves to the center, creating a differentiation process. We call them protoplanets, and then protoplanets collide and create even bigger planets. Okay, so at the end of this process, we ended up with the forming of the solar system, where rocky material was formed close to the sun. And further away from the sun, we see more of the icy materials and larger objects that accrete around little nodules. And these could be some rocky things that accreted out there. They could also be some icy planetesimals that came together, but they are also going to end up being large gas giants, because there's far more volume of material that they accumulate as they go around the sun than way out in the outer part of the solar system than in the interior part of the solar system. And so we have this beautiful array of 8 planets and millions and millions of other objects. These are asteroids. These are Kuiper Belt objects. These are comets, and that's the environment we live in. Well, if we take a look at the Earth over its 4.5 billion years, and we think about where did life begin, we believe it began fairly early. The rock record seems to indicate that microbial mats were starting to form about 3.8, 3.7, 3.8 billion years ago. All right. And so that's a long time. And then what happens is it's only in the last 500 million years that more complicated multicellular life really takes off. Now, this has been quite a discussion in many venues of why didn't more complex life start earlier? What was it that it took so long for life on Earth to really become complex? Does it take that amount of time, or does the environment have to change that then and for a period of time that is semi or pseudo stable, that then would enable more of the multicellular life to begin earlier? That's a very big topic right now in discussion, and I think what we'll see in my talk is we need to fold in the effects of cosmic weather. That means what the galaxy was doing to this area that we call our solar system over time in the past, to really tease out what might be occurring during those early parts of the evolution of life on Earth. So we do know in the rock record that over the last several billion years, the Earth was very cold. We call those events snowball Earth events. Now, this is a graph that talks about the times when we see in the rock record that the Earth was mostly ice covered. And the extent of that ice coverage, from 50% to 80 or 90%, is shown in this particular figure. And that occurs over several epochs. So, why did the Earth get so cold? What was the reason for that? And then, what were the causes that enabled it to snap out? These are also areas of big discussion that we want to know about. And we are coming to the impression that these events may actually be tied to more galactic environmental changes. These are perhaps in the realm of where cosmic weather is important to consider. Now, in this particular view, about 2.5 billion years ago, we had some really hefty events. And then about 2.3 billion years ago to about 800 million years ago, things were very stable. You know, the Earth was going through its normal cycles of evolution, etc., but not going through these climate extremes like snowball. So something happened that may have protected the Earth for long periods of time during this era that could also be contributed or considering cosmic weather as the potential cause for these not only snowball Earths but time periods where they don't occur. Well, let's put this in context and let's talk very quickly about the active sun. The sun constantly emits matter. We call that solar wind. It moves out in all directions. That's the atmosphere extension, if you will, of the sun well into space. And we're living in that atmosphere. Now, the sun goes through its normal evolution, so it has sunspots. These sunspots have huge magnetic fields that recombine, accelerate particles, and create enormous bursts of light we call solar flares. Sometimes sunspots, as they evolve, magnetic field erupts onto the surface of the sun and they reconnect and they create huge bubbles of mass. And we call these, in corona in particular, coronal mass ejections. And then following these coronal mass ejections, which blast into the solar wind, they create solar particle events. And so we're going to briefly talk about these. All right, solar flares. Here is what a solar flare looks like at many wavelengths. And as you can see, here's a sunspot on the surface of the sun in the far left. This particular sunspot is a quite large group. It's generating huge magnetic fields that are poking out of the surface. We see the surface of the sun where the spot sits. And if we go to a different light, if we go to the other panels, which are observing the sun in different wavelengths, then we see these intense flare events more obviously. These are accelerations that are occurring at a place where magnetic field energy is being annihilated and high energy particles are being created, and then they fly out into the solar wind. And here's another one for which we see what looks like the angry sun. All these, this is the observation of the corona. So this is an ultraviolet observation of the sun. And then all of a sudden, these real brightenings occur, and we call those solar flares. Now, we also see coronal mass ejections. All right. Now, here, to see these coronal mass ejections, we have a little circular mat that covers the sun. And then we put a little circle here to show you the size of the sun. But we block out the light of the sun. We only look at scattered light. All right. And in this scattered light, here we go. These are coronal mass ejections. Bam! There's a big bubble that goes. Here's
Tim,
another
I
one.
I
Wow.
hate I hate to interrupt, but I think you've unshared your screen, or somehow your presentation has gotten unshared.
Oh,
So
really?
maybe go back and share it again.
I can sure do that. Stop
Sorry
sharing,
about that.
and then we'll go over here and let me try this again. I wonder if the video is doing that. Did that happen during that during the one I was showing?
Actually, Jim, it's on my end. I'm so
Ah,
sorry.
ah.
So
Okay,
never
good.
mind.
Okay,
So
good.
sorry about that.
That's okay. Let me get back to it.
Yeah.
Okay. All right. So let's see a coronal mass ejection. Everything's working.
Yes.
All right. So these big bursts of bubbles that come from the sun, these indeed are called coronal mass ejections, and they're quite astounding. And when a coronal mass ejection comes towards the Earth and hits the Earth, it always produces aurora. So when you see aurora, you know we were hit by a coronal mass ejection. Now, here's another example of a coronal mass ejection, and it's off. We can see the sun shade is in the upper left of the figure, and the coronal mass ejection is going to go from that upper left to the lower right. You'll see it move quite quickly, and it's plowing into the solar wind. Now, what happens when it plows into the solar wind? It creates these solar energetic particles, okay, which are called SEPs, solar energetic particles. And it's a shock that as this shock wave moves from this rapidly moving hot gas into also hot gas, but not as hot, called the solar wind, it generates these particles, takes these particles and enhances their energy, and then fires them away from the shock, called SEPs. Now, let me show you what this looks like. All right, so here's everything's nice. There it goes. There's a fabulous coronal mass ejection. Now, what happens is when we see these particles accelerate, they move faster than the shock. Those particles will hit our instrument, and in the lower right, those particles are going through the imaging system of the instrument on this mission, which is called SOHO. It's a European Space Agency mission. And you can see these are really fast moving particles, and they were created by the CME. Now, in addition to these elements, the flare, the coronal mass ejections, and the SEPs, the solar energetic particles, there's another set of high energy particles in indeed the area around the sun, and we always are constantly worried about them, and they are called the galactic cosmic rays. Now, these are coming from the galaxy. This is part of cosmic weather. This is the part of cosmic weather that invades into the area dominated by the sun. Now, these galactic cosmic rays, we're not really quite certain where they come from, other than we think they're definitely coming from supernova. We have indication they're coming from other galaxies. This is why cosmic weather is a good term, because these other galaxies are connecting to our galaxy through a dark matter fiber, or filament it's called, and that sometimes enhances these galactic cosmic rays to follow that filament. They're seen in interstellar space, as I mentioned. They're part of cosmic weather, and their composition is mostly hydrogen. There are alpha particles, which we call the helium nucleus stripped of electrons. We call those alpha particles, and then electrons, and then heavier elements. Now, this might be iron with absolutely no electrons. I mean, a really hefty nucleus. And galactic cosmic rays are what we're really, one of the things we're worried about when we go out into space, because Well, they'll go right through your body. They're moving at enormous energies. You can see in this graph that the galactic cosmic rays vary in energy. They have this up and down spectrum. And there's more of them that get in during solar minimum. And that's because the magnetic field of the sun doesn't reach out extensively into space as much as it does during solar maximum. So our magnetic field of the sun is helping push these away. Okay, so now let's talk about this magnetic field of the sun, and it is called the heliosphere. And where we are, we're in what's called the local cloud. All right, so the image, this graphic that we've created on the right shows our heliosphere. All right, so our heliosphere is the area around the sun where the solar magnetic field dominates all the physics that's going on here. Okay, this is the extent of our magnetic field. Now, when the Voyagers passed by the outer planets and then began, because they had enough energy to continue to leave the solar system, we have found them go through several regions. They went through what's called the termination shock. This is an area where further out than the termination shock, we have a mixture of winds from other stars and winds from our own star mixing in the heliosheath. That's what it's called, the heliosheath. So the termination shock is the place where our solar wind, purely our solar wind, terminates and begins mixing with the winds of other stars that are in this cloud of material we call the local cloud. Then we end up going through the heliopause. This is the furthest extent of our solar magnetic field. And then beyond that, we encounter the cosmic environment. Okay, so Voyager 1 and Voyager 2 are actually encountering the cosmic environment now, and they are tasting the winds of other stars, if you will. And their experiments weren't designed to do this, but they are just barely making these observations and sending them back home because they are so far away. Voyager 2 is 150 AU astronomical units away. Voyager 1 rather is 150 astronomical units away. Voyager 2 is 130 astronomical units away, where 1 astronomical unit, or AU, is the distance between the sun and the earth. So we use that as a yardstick. So they are more than 100 times that distance away from the sun, and they are out into the interstellar medium and gases. Now, this is a very simplistic picture, and what we think is happening when we start doing the modeling might be some of these possible configurations of the heliosphere. So there could be a comet-like thing. It could maybe be a sphere. Maybe there's other clouds or something pushing on our sphere in a different way. Or it could be a croissant-shaped environment. And so the modeling has been going on for a while, trying to figure out, what does this heliosphere look like? Okay, that comet shape looks much like our own magnetosphere swimming in the sun's solar wind. That's why that was one of the early concepts. But I think the favored view of what this is this figure. Now, this is the croissant, and this has been done using huge computer models that are modeling this particular area. And we see the heliosphere then has this shape where we have material over the poles of the sun that seem to form the legs of the croissant, if you will. Now, one of the reasons why that's occurring is really shown in observations by Ulysses, which flew over the poles of the sun. And when it did, it found high-speed solar wind streams moving at more than 800 kilometers per second over the polar areas. Whereas at lower latitudes, in the plane of the planets, which is the line drawn through the center of the figure on the right, there's variable speeds, but it rarely gets anywhere near that high. It's more on the order of 300 or 400 or less kilometers per second. And so consequently, understanding the dynamics of the solar wind around our sun and mapping that into these fantastic models, we do see these what we would call jet-like features, and producing a heliosphere that's a croissant. All right, so that's the heliosphere. But what happens to the whole solar system, to the heliosphere as it moves around the galaxy? All right, and here's where much more cosmic weather concepts can come into play. It turns out we oscillate up and down the galactic equator. Okay, this is really a fantastic set of observations. What we're seeing is the galactic plane. That's where most of the stars are. So in other words, this is where most of the mass of where most stars are. So it has a huge amount of mass. And since we were born in a cloud above this galactic plane, those stars and the mass in the galactic plane is pulling us down. Now, when it pulls us down, we overshoot, we go below the galactic plane, and then we go back above the galactic plane. And we form this oscillation. So we go up and down about 6 times while we're orbiting the galaxy, which is about 225 million years is what it takes to completely go around the galaxy. Now that means, we're in and out of the galactic plane with a period of 70 million years, and we're moving through a variety of environments. We're moving through all kinds of different clouds. And so we see sometimes our heliosphere must get squished if we go through really dense clouds, or if we're going through spaces where there are little or no cloud material, then they would expand greatly. And so you see at the upper part of the cycle a bigger heliosphere, and then as we go to the galactic equator, it'll squish our heliosphere back and forth. Now, why is that important? Well, what's important about it is what some of the things that the Voyagers have found. Okay? Now, here's a plot of data from both Voyager 1 and Voyager 2. And we see it's measuring the cosmic rays, and then all of a sudden it gets into the heliosheath, and the intensity of the cosmic rays go up. And that's true for Voyager 1, and that's true for Voyager 2. Now that tells us these cosmic rays, which are trying to get into the heliosphere, most of them are stopped at the heliosheath, and therefore they don't get in. Okay? Now this is really a fantastic research result, because that means the environment outside the heliosphere is much harsher. 75% of all the cosmic rays that the Voyagers observe out in the interstellar medium don't get into the heliosphere. And these galactic cosmic rays have a number of effects that we're going to talk about on our planet, and certainly about traveling for humans outside our Earth and outside our magnetosphere. And so it's really quite an important set of observations. All right, So where's the sun? Well, the sun is in what's called the local cloud, and you can see the direction of motion that we're taking relative to the galactic center. You also can see heliospheres, in other words, what we call astrospheres. Those are stars with their own heliosphere. We call them astrospheres. So you see these astrospheres from these other stars all over the place. Now, that has to be the case because nearly every star type generates some sort of magnetic field, except for the really large stars. And so most stars are going to be creating astrospheres on their own. Some we can see, some we cannot see. And we can see these based on where those astrospheres are relative to how they're interacting with their interstellar medium. Okay? Now, what's happening as here's another view on the right of us moving out of the local interstellar cloud into the G cloud, and this G cloud is very different than the cloud that we've been in for the last several million years. Okay, so in the next 300 years, in the next 3,000 years, maybe 2,000 years, we're not quite sure, the sun's going to exit the local interstellar cloud. All right. Now, the interstellar cloud has very low density, and it's really the era of the modern humans. Most of the local interstellar cloud where humans have been walking the Earth is pretty benign. It provides us with an extensive heliosphere, which then cuts down on the cosmic rays. So for the last 40,000 years, which is the advent of the human species, which exploded during this time period, inventing agriculture and creating cities and dominating the other species of the world. This is really the era of modern humans. And the problem, of course, is as we enter the G cloud is going to be 30 times more dense than the local interstellar cloud, our local cloud. Pardon me. So the G cloud will squash our protective heliosphere, moving it in significantly. Now that means this highly inhomogeneous areas around us in density and temperature are affecting the size of our heliosphere, and this allows us to be exposed to a higher flux of cosmic rays into the inner part of our solar system. Now, this has been known for the last 20, 30 years, but how difficult these measurements are really indicate our lack of knowledge of what may happen. But here is some recent observations. You see the blue cloud is the local cloud. These are, this is a three-dimensional model. One can log on to a website with this model from the European Space Agency, move it around and see where we are in the local cloud, what's happened over the time, and then recognizing that we're going to be leaving this local cloud and moving into other areas. So this is a very important and hot area of research right now. Well, what's out there? Well, what's out there are remnants of stars, and we get those remnants of stars because stars evolve. As mass accumulates into bigger and bigger stars, as you can see in this graph, the y-axis has masses of stars. You can see the really big stars. Well, they very quickly, in tens of millions of years, which is not long at all, will go through a cycle, pardon me, create massive explosions through supernova, and therefore generate all kinds of other material, and other clouds of gas into space. And these clouds of gas will interact and be pushed around depending upon the magnetic field in some cases, particularly if these clouds have ionized material. The galactic magnetic field is shaping their size and a little bit of their motion and how they move through time. So these stars then, as they go through phases like red giant phase, the outer skins of these stars are very cool. They're very red. That means they're very cool. With the blue, it means they're very hot. But in this case, the red stars are very cool, and dust begins to be created. This is areas where dust is created just outside the red giants. They cool, so carbon comes together, forms graphite, silica comes together, forms silica dust, and then these giants go through a variety of phases, and as they shrink, their solar wind increases. That dust and material that gets created gets pushed out, and so they're constantly making material like this and shoving it into the surrounding areas. And then, of course, as the star has smaller mass, such like sun-like stars and red red dwarf stars or brown dwarf stars, those are stars that stay together tens of billions of years and also go through evolutionary processes that dump their material from the star into the intergalactic medium because they're generating solar winds and magnetic fields. Now, when we look out into space, we see all kinds of different material. These are examples of interstellar clouds. There's the dark nebula. Some of these clouds are cold. If they're cold, they start to coalesce. That means they're going to create molecules, and sometimes we call them molecular clouds because of that. But they're so dense that they block starlight behind them. So these dark nebula are just clouds of dense material that are cold, that are blocking the light of stars that are further away. All right. Then there are emission nebula. So here's a star that's gone through it's an evolutionary stage where it's gotten big and now it's gotten small and now it's starting to shed its outer layers. And we see these concentric rings. And then as you get closer to the star, you see the gases. You see the gases that are coming out in these big bubbles. And the bubbles are oddly shaped, but the concentric rings are evenly shaped, and those concentric rings are dust. So this is dust that's being made, that started out in the outer layers of a red giant. It as the red giant got smaller over time and went through its evolution, it started shedding that dust. And you can see it sort of did it in events. You see waves of that dust getting pushed out. And then finally, as we all move around the galactic center, stars move into areas where they can illuminate these gas clouds. And here is what we call a reflection nebula. So this particular nebula is being illuminated by stars that are close by and therefore exciting some of the molecules and matter that's in these clouds to radiate the light. And that tells us it illuminates what these clouds look like. Now, we also can look out at these other stars and see their astrospheres. And here's some examples of astrospheres. Some have long tails, some have some really oddball shapes, and that's all because of the environment they're in. Now, in the lower right-hand corner, this is a star that's plowing through a really dense interstellar cloud, which is estimated to be about 2,500 atoms per cubic centimeter. And indeed, if that happened to our star, our heliosphere would be less than 1 AU, and all the planets from Earth on out would be in interstellar space, which would mean that we'd be hammered by cosmic rays and the whole spectrum of cosmic rays. So this is really a dynamic environment. We're just getting knowledge of what's out there and trying to figure out where the sun has been and where the sun is going relative to the cosmic environment. And so the Milky Way environment, now we're going to talk about it on a more broader scale, and this would then tell us what's happening all around the Milky Way. And the first thing to note is when we stand back and we look at what we call the cosmic web, these are filaments of dark matter. Now we can't see the dark matter, but these filaments are where galaxies accumulate. All right. So all these filaments we create in our computers based on where galaxies are. So you can see the three little vignettes have one on the left side, galactic clusters, and then on the right side, what would be the dark matter that's holding that cluster together. And so you can see each and every one of those. And so we end up with this really complicated structure. Now, what that tells us is the dark matter is helping these galaxies form clusters. If these galaxies start forming clusters, they have, of course, their own massive gravity. And as they are moving out into the cosmos, if you can remember my lecture on cosmology, we're in an era of time when all of space is moving outward. The dark matter is starting bringing these galaxies together and forming ever larger galaxies. Okay? Now, I'm going to show you a simulation. Here's a simulation of our own galaxy. This is, we are a barred spiral. And the set of red stars is another galaxy that's coming in contact with ours. So this simulation, we'll see what happens, and we get to look at it in a nice three-dimensional view. And here comes another galaxy that we are bringing in, and indeed, these stars pass through us because we're larger. We disrupt it. It also disrupts us. Pardon me. And we form a consolidated set of material we now call the galaxy. And you can see these different color stars come from a different galaxy. And we work really hard to identify them. In fact, we've begun the process of looking at stars and identifying them as being out of place. Now, out of place means they have different compositional elements associated with them than the neighboring stars. So that means they must have come from another galaxy. By doing that, we see that our galaxy has absorbed several other galaxies. All right, so here are stars with different metallicities, it's called, it's different compositions. More metal in some stars than in others, meaning they must have had a different origin. They're now mixed in with ours. The blue stars are from Shiva. The yellowish stars are from Shakti, and they are also shown. Now, also what happens is as these galaxies merge, they also form shock waves or gravitational waves. We're just now learning more and more about gravitational waves. Well, gravitational waves can push clouds around, and these molecular clouds then from a wave can collapse and form other stars. So not only are we bringing in stars from another galaxy, but we're also taking gas in our galaxy, shoving it together, and interacting it with gas from these other galaxies, forming new stars. The latest data from Gaia seems to indicate some more fascinating things. Here is all the galaxies in our area. As you can see, the galaxies have tugged and pulled on our galactic plane. It's not flat. It's not exactly like a flat pancake, but the sides are warped. And that's because of the gravitational interaction with other galaxies. Now, last year, Hubble observed some really fabulous material that you see here in red, along with other notable points. Quasars, A, B, and C, these are important because from the quasar light that's passing through this gas to us, we're able to understand where it's going, where it's coming from. All these things are important. And what we're finding out is most of this gas is falling on our galaxy, being sucked out of the small Magellanic Cloud. All right. So all this gas, we're looking at it as it's coming into our galaxy in this view. So this is really spectacular. So our Milky Way is really quite a complicated set of stars that evolve, gravitational waves that occur, promoting other stars to be made. It also, at the very center of our Milky Way, which we're moving towards here, has the spectacular black hole. We're orbiting around this black hole. So these observations really are all about the large scale objects all around us in the cosmos, and they produce its own weather. Now, here's a summary of what I've been talking about. We have space weather from our own sun. We have solar magnetic fields. You can see that's yellow. Also, what's yellow is our own solar wind and energetic particles. But when these particles hit the heliosheath, just like a coronal mass ejection, that front causes acceleration. These particles are combined with the interstellar neutrals that come floating into our galaxy, get ionized by the sun. The solar wind pulls these interstellar neutrals that have now become ions through a process called pickup and drags them back out to the heliosheath, where they're accelerated and create a very high energy portion of the cosmic ray spectrum that we've identified, and we call it the anomalous cosmic rays. So our heliosheath generates anomalous cosmic rays that shoot into the interstellar medium, and that's our contribution from space weather into our galaxy. But our galaxy, the cosmic weather, is the interstellar magnetic field. The dust particles that come in, some that are large can come right in. Smaller particles that are charged don't make it in. We have high energy cosmic rays that make it in, but the low energy cosmic rays don't make it in. We have interstellar gas and plasma, we call it. These are ions and electrons. And they're all part of the environment where there are molecular clouds. And now we see these intergalactic winds that are coming in. They're being dragged into the magnetosphere. So this is now emerging as a major field of study. Now, space weather changes on the time scale of hours and days. Cosmic weather changes on time scales of thousands of years to maybe millions of years, okay? And so it's an environment, as we see here, that we believe has occurred since the dinosaurs walked on this planet, of going through a very dense interstellar cloud, about 100 particles per cubic centimeter, which squishes our heliosphere to less than an Earth radii, popping our planets out into interstellar space. So we go from the bottom figure, where we see a huge heliosphere today, protected by the local cloud, to a very dynamic system where the interstellar cloud has really hammered our heliosphere, squishing it, popping out our planets into the interstellar medium. Now, is that okay? Well, it turns out it's not okay. When these things happen, we have huge effects of on our atmosphere. And this is where I'll end in the next couple charts. So these high energy particles, galactic cosmic rays, hit our atmosphere now. Now there's more and more of them. They bust up our atmosphere into smaller particles. We some of which become radioactive, like carbon 14 is made in this process. We believe some of these galactic cosmic rays produces an increase in low clouds. This process of spallation and interaction exerts a major effort, change in the troposphere, creating low-lying clouds, which of course reflects solar radiation, which then moves the Earth into a cooling environment, and perhaps was one of the reasons why we went through Snowball Earth. We also, if we pass through a dense molecular cloud, so this has got all kinds of hydrogen in it and helium in gas form, what happens is the plasma portion of it shrinks our heliosphere, and we get bombarded by the neutral hydrogen, and that neutral hydrogen interacts with our ozone, destroys it. It also, there's a strong depletion of oxygen, and there's a huge global climatic change that occurs. Now, we do know that that has happened. About 65 million years ago, we measured in ancient amber a very depleted atmosphere of O2. And this is the key explanation for that. There's no other explanation. It's a global phenomenon, happened all around us. We had to figure out how all of a sudden the oxygen changed like this. And it is one of the leading ideas that we flew through a molecular cloud. Okay. So let me just review. Galaxies are large collections of gas dust stars that are constantly evolving. Stellar explosions create clouds. Galaxies merge, sucking more material, gas, and dust, causing more stars to be made. Our sun is a star in a Milky Way, which generates space weather in and around it, but it's also subject to cosmic weather. The space weather has a solar wind background, but we produce solar flares, coronal mass ejections, also solar energetic particles. And this changes on the time scale of hours and days. And then cosmic weather has a whole host of other things. These are interstellar gas, dust, galactic magnetic fields, and high and low energy cosmic rays, anomalous cosmic rays, along with intergalactic winds, and these change on much longer timescales. So if we think space weather and its effect is bad, that only happens over a very short period of time, and cosmic weather may have had radical changes in the Earth's past climate and the habitability of this planet. All right, thanks very much. And so, Jim, let me turn it back over to you.
Wow, Jim, thank you so much for just a really enlightening lecture. I have one question. Um,
Sure.
I think I think you said, and then we'll take questions from the chat. Um, I think you said that we were leaving our interstellar cloud and moving into, I think they called it the G cloud,
Yeah, it's also called the
yeah,
galactic cloud, the G
galactic
cloud.
cloud. So, I mean, I kind of imagine being in an airplane and flying through clouds of different types,
Right,
as you leave one cloud and it's clear for a little bit, and then you
right.
maybe enter a dark cloud that's getting ready to rain or something like that. Do we know the qualities of the cloud that we're getting ready to enter?
we are starting to, only because we recognize it's the importance of it. It's very hard to remotely sense, very
I
hard to
see.
remotely sense, because there's not what doesn't appear to be a lot of stuff going on. So there's no stars, huge hot stars that are illuminating large regions that we can see it. There's we have one of the most important measurements, which is its density. It's 30 times more dense than our local cloud, so it will squish our heliosphere.
Ah, yeah.
Okay, maybe to where Jupiter is.
Hmm.
Now
And then,
that
of course,
means we're going.
as you said, then when the heliosphere contracts, that exposes Earth to a different sort of radiation environment,
Right. Yeah,
right?
that we haven't had in the last 40,000 years.
Yeah, yeah. All right. Well, thanks for letting the moderator ask his questions first.
Of course.
Let's go to
How could
the
I how
let's.
could I how could I say no?
So Laluani, one of our most uh, faithful Book of Scientists attendees, asks, how common were galactic mergers in the early universe compared to today? And what does this tell us about the evolution of cosmic structures?
That's a good question, and I don't know the exact answer. All I can say is we have developed methods to tease out what we have merged with. And we know of at least three dwarf galaxies we've already eaten up. Okay. But there are, as the one figure I showed, all sorts of other dwarf galaxies all over the place. Now, those are being attracted to us. All right. And what's helping is dark matter is trying to pull all of us together. It's not just the mass of our galaxies that are attracting each other, it's also the dark matter that we have surrounding our galaxy, holding our galaxy together, that is attracting other galaxies and creating these filaments. And these filaments are paths that these galaxies are going to be taking. So when we do these computer models and we illuminate the dark matter and we see this web, it is really exciting to understand what's happening, and it is the paths that those galaxies will take. And in the meantime, those are the paths that we suck gas out of galaxies, okay, bringing it into our own galaxy, creating new stars. We suck cosmic rays from being generated in those galaxies to us. So our galactic cosmic rays, and we've known this for a while, contain not only high energy particles generated within our galaxy, but also from other galaxies.
Wow. Yeah. It's a complex universe we live in. Let's see. Sophia, I think she's looking for a little clarification.
Sure.
Um, she asks, is the local cloud around the sun? And is it like a regular cloud made out of water, or is it made out of other elements?
Yes, good question. The local cloud completely surrounds us. We've been traveling through this cloud for tens of thousands of years. All
I
right.
mean, our entire solar system is in it. Not
Yeah. Not
right.
just the sun, the whole heliosphere.
Yeah.
Now, what's in the heliosphere is, all the planets, all the Kuiper Belt, a lot of the comets. Now, some of the comets that we have, like in the Oort cloud, that's being attracted by the sun, kept with the sun, and it's moving with the sun. But those comets are out in the interstellar medium. Okay. And when we pass by stars and other things that are also in the local cloud, we perturb those and they come in. And then we see them and look at them, and we can tell their composition is also different than comets that may be on the inner part of our solar system, the Jupiter family of comets or the Kuiper Belt family of comets. And that spectrum has been modified by the fact that they're sitting out in the local cloud. And the local cloud is uh, uh, made up of ions, electrons, winds from other stars. Aspects of it are cold, so molecules are created. Those molecules indeed are water. Sometimes hydrogen creates a molecule called H2, hydrogen. Two hydrogens get together. And so there is quite an effort going on, particularly by JWST, that are observing clouds, trying to figure out their composition. Some of the compositions of these clouds contain amino acids. All right, and so they get cold enough that these carbon compounds come together, create chains, and those chains end up being amino acids. And so there's just quite a diversity of material that's out there.
Yeah. Julius asks, muons from cosmic rays have been used to discover what's beneath the Earth. As we move into denser GCR clouds, will this be good for this type of research here on Earth?
Yeah,
As we,
so
yeah,
muons are created when the galactic cosmic rays hit our atmosphere and blast it apart.
right.
Yeah, so the more cosmic rays, the more muons we're going to get. So,
Oh, that's a simple answer, huh?
yep.
Yeah. Yeah, if we're irradiated by more galactic cosmic rays, then there's a research opportunity in that because we'll get more muons to.
Yeah, provided we can survive the environment, which might have global climate disaster written all over it.
Yeah. Um, I don't intend to be around for that, by the way. Um,
Well, if you are like me, I want the human species to survive. And I mean
well,
not just a few million years. I'd like it to survive billions of years.
that's a
So
good point.
the more we know about our future, and I mean our far future, then the more we're prepared as a species to survive it.
And that's a good reason for why we continue to study today, even though these events may happen in millions of years.
That's right.
So, let's see. Lila asks, are we able to map what other interstellar clouds we've gone through in previous oscillations? Or does
Yeah,
their shape and evolution make that ever changing and not something we can backtrack with modeling?
we have started to backtrack. We can see a couple clouds that we've been through, but indeed, as you point out, because that whole environment is constantly changing, we can't tell exactly how big these are, how long we went through them, and it's even more difficult the further we are away in time from when we pass through them.
And Laluani has a follow up. Let's see. How do stars produce heavier elements? For example, carbon and iron and that sort of thing.
Yeah, that happens in the very interior of the star. Einstein started the whole concept with his equation E equals mc squared. It means energy equals mass and then a constant times a constant. Well, that means we can create new mass given energy, and we can create, therefore, new elements in the very center of stars by squishing them, keeping their motion from allowing them to dissipate. Their temperature goes up. That means we're giving them more and more energy. They combine, hydrogen combines and creates helium. Helium combines in the very center of stars, creates carbon. Carbon combines in various ways with other elements that are also there that are created, the helium and the hydrogen, and creates oxygen. So that creation of elements goes up the scale all the way to iron.
Wow. Yeah.
And
And
then
does
when the
that
star
all
explodes, all that material is poured out into the galactic environment.
exactly? And then it does it begin again, only with
Yeah, it
heavier
begins
elements.
again. Yeah, except now it's got aspects of other material.
Right.
And that
Right.
other material creates planets and creates us. So we weren't created at the early stage of the universe. It took many billions of years before the environment was such that this other material was available to create planets and therefore create an environment where humans, more complex organic material, can be alive and roam the environment.
Julius is back and he says, what radiation exposure from GCRs do we experience here on Earth, like per day? Will this change as we move into I presume he means the new galactic cloud?
Yeah, it will go radically up when we go in
Okay.
the galactic cloud. We can tell when there are important events that happen by analyzing tree rings. By analyzing tree rings, what happens is we get a storm of high energy particles hitting our upper atmosphere, which actually generates various types of isotopes. Isotopes meaning um, adding extra neutrons to the inside of a nucleus. And so we can actually create carbon 13 and carbon 14 out of carbon. Carbon has 6 protons and 6 neutrons. That's carbon 12. But when you add another neutron, it makes it 13. When you add another neutron, that makes it 14. And that's unstable and is radioactive. But trees don't care. Trees will suck in carbon 13 and suck in carbon 14. And so that ends up in their tree ring. And you can look at a tree ring and see the radioactivity from a tree ring must have been an enhancement of high energy particles. Now, that enhancement of high energy particles are more likely than anything else solar energetic particles. But you can think of that happening if more galactic cosmic rays were able to get to the Earth because we've moved into a more dense molecular cloud.
Yeah. Um, Lalawani says, how do you understand the heliosphere impact for future space exploration missions? What is that going to do to us as we, go to Uranus and Neptune? And you and I just spent time writing a paper about, you know, the future of
Making sure
planetary
we are able
exploration.
to do that, yeah.
Yeah.
Well, for humans, it's a bad deal unless we begin the process of using the new medical environments that are being created that help repair genes, help repair our DNA. Okay. And that's critical because cosmic rays can go right through the body, kill every cell between when it went in and when it went out. Okay. And our body will have to reproduce those. Now, when they reproduce them, you want them to reproduce those cells correctly. If they reproduce those cells incorrectly, we call that cancer. And so, a higher flux of material like galactic cosmic rays constantly bombarding the body and not able, having the body able to reproduce those dead cells, getting rid of them and reproducing those dead cells, will do one of two things. One, cause cancer later on in life as the body is trying to live for longer periods of time and replace those cells. Or two, it's high enough that it just kills you outright. You have organ failure, and that's the end of it. So, space travel by that time in 2,000 years will be very different than it is today. We'll have all sorts of DNA repair mechanisms. And so I think we'll be able to be genetically engineered to withstand the higher energy environment outside our atmosphere by that time. That's my
Or we
prediction.
may not look like ourselves at all.
May not, I don't
We
know.
might be something totally different. But it shouldn't really impact the robotic missions that we're sent, like the Voyagers and the New Horizons, um, right? If we end up
Yeah, right.
continuing to explore using robots. Yeah. Um, okay. Well, thank you, Jim, for this fascinating lecture and for the opportunity to wrap up Book of Scientist so intellectually. We we appreciate the stimulating thoughts that you've got, and how all of that ties in from everything we've been talking about on Book of Scientists, space weather and cosmology and the James Webb Space Telescope, and now the greater picture from the Milky Way. So starting with Nicole and Julius and Lila and Heather, all say thank you so much, Jim.
You're very, very welcome.
Right.
And
I'd like to
maybe,
remind,
just maybe, in the second environment that happens, I'll get invited back.
yeah, I can guarantee that.
Oh, all right.
Um, in fact, I remember. So here, I'll just tell a little story about you as we're wrapping up here. I remember having coffee with you when we were back in June when we were setting up the curriculum, and I had
Uh-huh.
a list of I don't you remember it was like 16 different topics, and you took a look at it and you said, well, I'll do this one, and you signed your name next to it, and I'll do this one, and you signed your next, and I said I had it kept going, and I said, well, wait, Jim, I got to make room for other guys too. But yes, we
Which you
love
did.
having, yeah, we did, and it turned out to be a great success. So we love having you on, and I'm sure next semester is going to be exactly the same. So to remind everybody, Jim's put together a quiz. We think we've got the grading mechanism working properly this time. So go take a quiz, pass the quiz, and you can get a certificate of participation. Thank you, everyone, for being part of Book of Scientist in 2025. And with that, we're out.
All right. Thank you so much, Jim, for the invite.